Hey guys, here's a question about latent heat of fusion in particular, and this relates to a quiz that I know some of you are working on right now. So I want to go through how to use this tool right here and how it relates to this tool right here that you've been working on using in the past. So let's get into it. If this is a standard heating curve, and we're talking about water with ice melting in the water, this little thing here is representing ice, that angular figure, and this represents a beaker of water, and that represents warm water all around the ice, and the arrows represent that heat is going into the ice to melt the ice. Okay, you guys did a lab on this recently, so think back to your experience melting the ice in hot water, and we'll move on from there. Okay, so this is our heating curve for water. You might call it a phase change diagram because it's a diagram that shows phase changes. But if this is water, we see these two plateau sections, so one here, one here. Generally the first one represents where the heat of fusion applies, that's where melting is happening. The second one shows where vaporization is happening. And the reason, again, just a quick reminder, the reason why it's a plateau is because on our y-axis, we have temperature, and the x-axis we have time. You are adding time generally, but we're also adding heat. So as you're adding heat constantly in this direction, generally you either increase temperature as you increase heat, that's why there's a positive slope here, or as you increase heat in certain situations at certain temperatures, certain special temperatures, there becomes a plateau section. So in this case, the first plateau is generally where melting would happen, phase change from solid to liquid. And if this is water, the phase change for water, the melting point happens at 0 degrees Celsius. So let's say this is temperature in Celsius, this is going to be 0 degrees. Normally I'd write that on the left side of my scale, but there's not much room, so I'm going to make it work. Okay, so that means that at 0 degrees Celsius, from here until here, there is a certain amount of heat that must be added to fully get a piece of solid ice that is any number of grams in this case to be fully liquid, but still water. Okay, we haven't changed the substance, it's just was solid, now it's liquid. Okay, so if we say that this is 1 gram and 1 gram, then when we are trying to find out how much heat was required to go from here to here, this ends up being called our latent heat of fusion. Latent heat of fusion. It's the total amount of heat required to go from there to there through the entire phase change. If you go from solid and you melt it halfway, you get here, that's not considered latent heat of fusion. That's part of the latent heat of fusion. You've added a certain amount of heat, but it's not considered the latent heat of fusion. Okay, so the full phase change is really important. And latent heat of fusion values are units of heat, units of energy. So we report them as a joule value. But if you think about this, let's say you have a small ice cube versus a really, really big ice cube, right? Maybe 10 grams, maybe 20 grams, maybe a 10-pound ice cube block. That's a lot of ice. But in this case, which of those is going to require more energy to melt? A small block of ice or a really big block of ice, right? If you think of that intuitively, the big block of ice is going to take way more energy. So therefore, it makes sense that mathematically, the latent heat of fusion to fully melt this block of ice versus that one, it makes sense that those two latent heats of fusion should be different. Okay, it makes sense that this one should be larger than this one. Okay, so we're talking about heat of fusion values, and we annotate that often with an H sub F. H sub F, then this heat diffusion should be bigger than that one. Okay, and so the way that we mathematically manage that is by having this joules per gram right here, having the gram component to it. That's just saying that the joule value that you calculate for heat diffusion depends on how much mass you have of that substance. Okay, I apologize if the camera is wiggling a little bit. I have a stand set up and it's a little bit wiggly. Okay, here we go. So that's a little bit of foundation of what heat diffusion is. So now let's look at this thing, because I know some of you were like, what, how does that work? What do we do with that? On the bottom of this, these are some really basic instructions. Solve for 1, 2, 3, then 4. 4 is, there's our H sub F, heat diffusion for ice, okay? But again, a heat diffusion value is generally going to be a standard value in joules per 1 gram, okay? And so what that means is that we're gonna have to factor mass in somewhere when we get to this calculation. And that's what this M of ice is for. Okay, so the mass of the ice. I know it looks like mice, it's kind of fun, but mass of ice. Okay, so let's reset our board and then we'll start doing some math. Reset board. Here we go. So now, let's say we have a mass value that is, let's say the mass W, that's the mass of our water. Mass of hot water. Okay, let's say mass of hot water is, I don't know, let's say it's 10 grams, 10.0 grams. Okay. TI stands for T initial. So TI is initial temperature, and TF is final temperature. Okay, so during our heat calculation, you have to find delta T. Delta T is the final temperature minus the initial. It's kind of like saying, okay, let's say you went for a run and you ran really far. Okay, you started here and you ran all the way over there. Okay, if you want to calculate this distance, right, you have to take the final position, whatever number of meters that might be, and subtract the initial position. So maybe this is like 15 meters and this is 10 meters. If you want to find the difference, then you take one minus the other. Okay, so this would be a 5 meter distance. It's the same process for temperature. Okay, you take temperature final minus temperature initial. So let's say our initial temperature is, in this case, like 70 degrees Celsius. And let's say our final temperature is 62 degrees Celsius. Then in that case, our delta T would be 70 minus 62 is 8. Okay, so now we have our MW, so that's effectively what goes there. We have our TI, our TF, so we can calculate the delta T. And we already know the specific heat value for water, 4.2 joules per gram per degree Celsius. We know the gram, we know the degree Celsius. So now we can figure out how much heat must have left the water in the process of the water cooling down. Okay, so if the water cools down, it means that that energy, that heat energy, must have gone somewhere. Okay, and if we observed that the ice was melting, it means that the ice must have been absorbing some of that heat. Okay, so let's go to the next thing. Okay, so we have our mass of hot water, and we have our delta T, MW, we have our delta T. So now let's find QW. QW equals 4.2 joules per gram per degree Celsius times 10 grams times 8 degrees Celsius. Okay, get rid of these. So now let's use maybe a different color. So now we can cross out our gram units, because this one's in the numerator, that's in the denominator. We can cross out our Celsius units, numerator, denominator. And now we only have 1 unit, which is good because we want our heat value to be in units of joules. So now we do a little bit of math. And this is where it'd be really good for me to have a calculator. Okay, 8 times 10 is 80. So this is 80 times 4.2. Let's just do this the old-fashioned way. 0, 16, 0, and that's not the right number. Okay, 0, 6, 3, 3. Okay, so our QW, let's go back to black because the orange is too wide. QW equals 3360 joules, if I did my math right. Apologize if I didn't, but let's go with it just so we have a number. 3360 joules. All right, so that is the amount of heat that went into the ice. So now, here's the thing. If our ice melted totally, and we're assuming that no heat was lost to the environment, or we're really assuming that there's insulation, there's thermal insulation on the sides of here. So no heat can be lost, but no heat can come in either. So if there's ice melting, that means there's heat going into it. So where is that heat coming from to melt the ice? It must be coming from the water. Okay, so that means that if our Q water is 3360 joules, then our Q of ice must be the same magnitude of this. Okay, technically, if we were reporting these numbers in an accurate way, we should say that the heat that goes in to the ice has one sign, positive or negative, and the heat that leaves something else has a positive or negative. So technically we should say that this is negative 3360 joules, or actually it would be the other way around. We'd say that the water lost that many joules because it gave it away, and the ice gained that many joules. And now that I'm looking at the numbers, it's a little bit funny. The numbers, the sign doesn't quite make sense the way that we've set it up. And we haven't talked a whole lot yet about changing mathematical sign based on what direction you're moving in, if you're the heat. So I'm not going to worry about that right now. Let's just recognize, the most important thing is to recognize that these are the same magnitude of energy. So all of the heat that came out of the water went into the ice. And yeah, apologies to any of you who are really frustrated that there's no negative sign on one of those. But for now, let's just acknowledge that the magnitude is the same. So going on to here now, again, we're looking for our standard heat diffusion. We're trying to figure this out experimentally, okay? You could look up what the standard value is, like the actual scientific value, but we're trying to see if we can figure this out on our own. So we go back to our mass of ice, right? Actually, we didn't have this before. We had the mass of water. Let's say the mass of ice is, let's say there's also 10 grams. That would make our numbers work out well. Okay, so if the mass of ice is 10 grams, and we know that the Q of ice, so the heat that went into the ice, is 3360 grams, then we just use this process. Okay, this is showing that the heat that goes into the ice is a function of this property, heat diffusion, which is basically saying how much energy is required to fully melt 1 gram of ice, and then we multiply it by the grams because it turns out that grams matter in this case. If you have more ice, it'll take more energy overall, okay? And if you have less ice by grams, it'll take less energy. So here we have 3360 grams times, or equals 10 grams times, oh sorry, this is 3360 joules, equals 10 grams times our heat of fusion in units of joules per gram. Okay, so what we do is we can divide this side by this side. So let's divide this by 10 grams, cross that out. We end up with our heat of fusion equals 336 joules per 1 gram. Okay, and that's how you do it. There you go. And then later on, what you would do is you would compare this to the known scientific value of the heat of fusion for ice, and you can calculate percent error. So how wrong or how inaccurate, how off the mark was your experimental calculation, but that's for something later. Okay, this is just the basic process of thinking about how the heat leaving the water is the same as the heat going into the ice, and then you can use whatever your data is to calculate your own heat of fusion. So we're trying to establish a standard value using this process. All right, hope that was helpful. See you guys soon.